Hi, folks. This time we're going to talk about the acid-base neutralization reaction. When acids and bases react chemically together, they neutralize, they counteract each other. And this is one of the useful and really important chemical reactions between an acid and a base. Back when we were talking about different types of chemical reactions, one of the types that I talked about was an acid-base reaction. Now, an acid-base reaction is a type of double displacement reaction. And so depending upon what book you're reading and how reactions are divided into categories, sometimes acid-base reaction is separated from double displacement and sometimes it is not. I like to differentiate it primarily because it is so important, but it really is a double displacement reaction. An acid-base reaction is an acid plus a base, and when they react, it produces water and a salt. The hydrogen and the hydroxide of the acid and the base combine to produce water, and then the leftover positive and negative ion combine to produce a salt. So what you actually end up with is a salt water solution. The acidity has been reduced, the basicness has been reduced, and typically you end up with something that is more gentle, and you have reduced the often hazardous challenges of both the acid and the base. Now let's try and predict the products of an acid-base reaction between sodium hydroxide and sulfuric acid, two very strong acids and bases. Now, sodium hydroxide and sulfuric acid are going to divide like this. The hydrogen and the hydroxide are going to combine to produce water, H2O liquid. And the ions are going to produce salts. Now, sodium is a group 1 compound, and group 1 compound's most common ion is +1. SO4, let's take a look at our chart. SO4 is sulfate. Sulfate has a charge of -2. When we ionically bond, we crisscross, so we are going to end up with Na2 SO4. The 1 comes down, we don't write ones, and we do not have to put parentheses around single polyatomics. So we're going to end up with Na2 SO4, and acid-base reactions typically are going to occur in a water solution, so it is aqueous. So this is our acid-base reaction. And let's go back and practice balancing. 2 hydrogens, and we have 1, 2, 3 hydrogens. Oh, let's not start with our hydrogens then. 1 sodium, 2 sodium, so I'm going to put a 2 here. That's going to now give me, let's see, I'm going to have to go 2 to give me 4 hydrogens, 1 sulfate, 2 sodiums, 4 hydrogens, and 2 oxygens. I think I am now balanced. It was as simple as that. I now have a balanced neutralization reaction. One of the other acid-base reactions that is relatively common because we do it to ourselves is when we take some sort of an antacid. Our stomach holds a weak solution of hydrochloric acid as part of our gastric juices. And when a person experiences heartburn, some of this acid actually leaks into the lower areas of the esophagus. This can be painful, and this pain can be reduced by reducing the quantity of acid. So for example, if you happen to take magnesium hydroxide, milk of magnesia, the magnesium hydroxide plus hydrochloric acid in the stomach breaks apart. The hydrogen and the hydroxides combine to produce water. The magnesium and the chlorines combine to produce a salt, and you end up with a salt water solution. If we take a minute and try and balance this, let's take a look. 1 magnesium, 2 chlorines. To get 2 chlorines, I'm going to go 2 there. I have 1, 2, 3, 4 hydrogens, so I'm going to have to go 2, 4 hydrogens. I have 2 oxygens, 2 oxygens. I think I'm balanced. I think it was, again, as simple as that. Another real common neutralization reaction that a lot of people have done in their kitchen is baking soda and vinegar. It's a fun reaction. It produces carbon dioxide gas. The acetic acid and the sodium bicarbonate also produces a sodium acetate. This is your salt. It produces water. It also produces those lovely carbon dioxide bubbles that are fun and are useful if you want to produce carbon dioxide for carbon dioxide homemade fire extinguishers and things like that. I want to spend a quick couple minutes talking about a limiting reactant. We have not spent a lot of time with this in this basic chemistry course. But a limiting reactant in a chemical reaction is the thing that limits the amount of product that can be produced. It's the reactant that gets used up first, and it limits the total amount of product that can be produced. When that reactant is used up, the reaction stops. So let's use the analogy or the example of a bonfire. You're making a lovely fire. The chemical reactants are wood and oxygen. So you pile wood up and oxygen is used from the air. Well, hopefully in your bonfire, you are not using up all of the oxygen molecules on planet Earth. So when does the bonfire burn down? The bonfire burns down when the wood is gone. If you want the fire to continue, you keep adding logs to the fire. But before you go to bed or you leave your campsite, you make sure that it is totally out, and sometimes you cover it with dirt to prevent the oxygen from reacting with what is left. But the limiting reactant in this reaction is the wood. There is an abundance, thank goodness, there is an abundance of oxygen. So that is not the limiting reactant, because there is lots of it. 21% or so of our atmosphere is made out of oxygen. But the wood, that is the limiting reactant. When that gets used up, the reaction is going to stop. Here's a couple other examples. The classic, you can never buy hot dogs and buns, it seems, in the same number per package. Let's say you buy some bratwurst or frankfurters and you have 5 in a package and you have 4 buns. Well, what's the limiting reactant limits how many you can produce? Well, it's going to be the buns. You only have 4 buns, so you can make 4 hot dogs and you're going to end up with an extra hot dog. If you're going to manufacture cars and you have 8 car bodies and 48 tires, you can make 8 cars, but you're going to have 16 excess tires. If you happen to be doing a chemical reaction, the challenge is the extra stuff floating around inside of the vessel. That's going to be impurities. And impurities, sometimes you don't care, but usually you care. And the impurities are going to be a challenge in any sort of a manufacturing process. This is the reason for balancing chemical equations. This is the reason for stoichiometry. And you've got to put in exactly the correct amount of each chemical to make sure all the reactants are fully used. There are no impurities in the final product. You don't want a limiting reactant. You want all of the reaction to go to completeness. And you don't want any leftover chemicals, because remember, those are going to be impurities in the product that you're making. This is one of the big challenges in street drugs. People who are making their own methamphetamine or anything like that in their garage, they do not know stoichiometry, and so they are going to come up with this stuff that is going to be full of impurities, and the impurities can cause, besides the drugs themselves, the impurities can cause a lot of harm. And so it is bad chemistry, besides being a bad idea. To fully neutralize an acid-base reaction, you've got to have the correct amount of each chemical to complete the reaction. So For example, if you happen to have some acid reflux and you take one Tums or one Rolaids and it doesn't do it, you take another one. I don't know about you, but I don't get this often, but once in a while, and you go, that didn't do it, you take another pill. And the reason is because you have to have the correct amount. If there is an acid spill, an industrial acid spill, you do not throw 1 tablespoon of baking soda on it. They add enough deterrent until the whole thing is completely neutralized. That's how it works. If you have ever played with the baking soda and vinegar reaction with your family, it's kind of a fun reaction to do. It's very, very harmless. But after you mix the two things together, it will eventually stop, but you can continue it by adding more baking soda. Then you add more vinegar. Then you add more baking soda. Then you add more vinegar. You keep adding reactants until you just don't want to anymore, because you keep adding reactants. It will keep going until you have reached that limiting reactant level. And once one of the products is used up, the reaction will stop. I've got to share with you one of the things that amuses me. All over the internet, there are lots of helpful hints on how to clean things with vinegar and baking soda. And they say, and this is just a few things I found, some screenshots I just clipped, how to clean windows with vinegar and baking soda, how to get clean showers with vinegar and baking soda, many things to clean with vinegar and baking soda. Okay, look at this from a chemistry standpoint. Vinegar, baking soda, you are making water and a salt and bubbles that are going to go away. So what are you actually cleaning with? You are cleaning with salt water. Yeah, you are really cleaning with salt water. So why do people do it? I don't know. I think they feel like Hermione Granger and they like pretending they're making potions, and the potions are cool. After the neutralization reaction, depending upon how much of whatever they have used, if you have a little extra baking soda left over, you might have a base solution. And if you have a little more vinegar left over, you might have an acid solution. But trust me, either one of these alone is going to be more powerful than mixing them together, because if you mix them together to clean, you are cleaning with salt water. Yeah, no. Bad chemistry. Bad chemistry. All right, see you later.